Okay, so I thought I'd talk today about reinforcement learning for generative artificial intelligence, and not going to be a particularly technical talk, but more one where I want to share with you some thoughts on the subject and some experience I've accumulated over the past year or two looking into this. And part of the reason is I think that our community here could uh, play an important role in this space. And so this is sort of an exploration of uh, you know how we could start thinking about some of the issues arising in this area. How do I get to the next slide here? Wonderful, thank you. All right, so before getting to this subject, I wanted to mention that it really is an outgrowth of a couple areas where the field of artificial intelligence has celebrated great accomplishments over the past few years. One is in reinforcement learning, and the other is in large language models. So in reinforcement learning, the picture is involves designing a reinforcement learning agent that interacts with an unknown environment, taking actions and getting back observations and trying to improve behavior over time. And in large language models, the picture is where you have a autoregressive model that takes in a sequence of recent tokens, symbols, so to speak, and then predicts what the next token is going to be, where the prediction is in a distributional form, assigning a probability to each possible next token. And some milestones in this area of reinforcement learning agent design involve, beating humans at Go, chess, shogi, and arcade games, among other things. And an interesting milestone in this area of large language models is when they realize that when you fit one of these autoregressive models to large swaths of text from the World Wide Web, you can end up with a model that you can use to simulate and generate extensions to any text you give it. And such models, early milestone in the space involve noticing that such models can complete documents for you, or if you feed in a document and tag on TLDR, which means too long, don't read, I want a summary, these systems actually will present a one paragraph summary to you of the document. So those are quite impressive things that came out of these autoregressive models. And one issue one feature that's shared in both these areas is scale. What really fueled these success stories and drove these milestones home was the scale. In reinforcement learning, we were talking about simulating for trillions of time steps in order to get performance we want. It sort of died or something. Or maybe the screen froze, I'm not sure. Started working. Got it. Okay, so with large language models, we're talking about models, autoregressive models with many free parameters, many neural network weights. And these days we're approaching on the order of 1 trillion neural network weights. Okay, so at some level, this reinforcement learning area, these successes can be thought of as simulation optimization, but on steroids, so to speak. And the large language models are autoregressive. autoregressive models on steroids. Also, these have branched out into various application domains. Reinforcement learning has been applied in various things like these to great success, and large language models are routinely used today to generate content for all sorts of things. Right? And these ideas today are coming together to drive some really impressive modern AI systems. And one of the areas this is really driving is what's now called generative AI. And the idea with generative AI is you have an agent that is fit to data from the World Wide Web, the huge amounts of data, an agent that encodes a neural network with huge numbers of parameters, like 1 trillion parameters, fit to data from the web, right? And in that process, the agent, you can think of it as growing a huge brain, so to speak. And then after that, you train the agent through letting it interact with humans and getting feedback on whether humans find it to be doing a good job or not. And through these interactions, the agent gets smarter and smarter. And these agents have been trained to produce things that are useful to humans, including text. So you probably heard about ChatGPT. That's the latest chatbot released a few weeks ago that is quite impressive in producing text. These systems also produce art, produce code, program for you, and can even do mathematical proof. Okay, so it's pretty impressive that these systems can now compete with humans in generating content of these sorts. Now, these systems are far from perfect. It's easy to find ways of fooling them. But if we take a glass is half full mindset, you'll see that the number of impressive things that these systems can do is really mind-boggling. Right? And we're actually, this is a slide I prepared like 6 months ago for another talk when this sounded futuristic, but today it's actually already here, right? We're worried about students not writing their own papers. Okay. What's that? Okay, so where's this all heading? Well, there's this vision that a lot of people have that, these technologies are going to improve over the next few years. And where we'll be in a few years is that everybody will have their personal chief of staff. Okay. So the idea is there could be some kind of multimodal interface. Here's an example of one possible form factor. It's a set of glasses with a speaker and microphone and video camera. And so you could have a multimodal interface of some sort that can see, hear, and sense everything you do and more, and can communicate with you by speech, video, or possibly a brain interface along the lines that was mentioned earlier. And this thing could access the World Wide Web and cloud compute, and do fast inference, reasoning, and recommendation for you. It can do things like fact check your writing, make a website for you if you want a website made quickly, monitor your health and advise you. Or there's a scene from The Matrix where this character learns to operate a helicopter very quickly through a upload from a computer. But maybe this is going to be reality soon, where you can get in a helicopter and say, "Hey, I haven't done this before. Can you guide me?" Okay. All right. And I have seen a colleague of mine do exactly that for cocktail mixing. Basically, you can have these glasses, see what's available in your liquor cabinet, and then you can discuss what you want, and it can advise you on what to do. Not far from this. Okay, and this is attracting intense research activity. Many technology companies are investing heavily in this area, trying to push toward this sort of vision. And there's a growing set of startups in this space as well. And among startups, it's one of the spaces, probably the space that's attracting the largest amounts of funding these days. All right, so with all this in mind, I think it's interesting to reflect on what I would consider short-term versus long-term research. Um, you know, and part of my point here is what's going on in this space. Because there's so much progress being made and so much in terms of resources and competition to make progress here. I consider most of the research going on as being short term, where ideas tend to focus on minor changes in existing engineering infrastructure, incremental improvements to algorithms, and generating impressive results. This process of short-term research has been generating really impressive results, and things improve over time. So there's no reason not to keep doing this. And I think it's great that we have this enterprise doing this. But I think as a community, of scholars, as you guys are here, it might be interesting to contribute to this a longer-term research agenda as well. And in particular, I think there's a role to think about what's possible rather than what's doable right now or over the next 6 months. And how to measure and maximize the performance of these systems in some fundamental way, and what the fundamental limits are, right? So I think there's not enough thought being given to this stuff, and you guys could do this. And this sort of conjures, the trajectory of work in information theory and communication, where, in the 1900s, there's a lot of progress being made in amplifying, boosting power so that it could transmit single signals over longer distances, right? A lot of hackery, even a Nobel Prize to Marconi in this space for his ability to generate power, right? And so maybe we're in this phase of the era of generative AI, right? And what happened is in the 1940s, Shannon and others came along and tried to work things out in a more fundamental and way, coming up with a unified theory of communication and information, and that's all very interesting. And it took maybe 40 to 60 years for that to really bear fruit in the form of physical products and devices that we use. But still, it's hard to argue that it wasn't worthwhile to think, even if that wasn't going to generate something useful within the next year. Okay, so it could be that we're in this phase, and there's need for an enterprise with this kind of long-term thinking. Okay. All right, so with that in mind, I don't know how many of you are familiar with how generative AI today is being done. So I thought I'd share a few thoughts on that. So the first step in developing these systems involves pre-training. That's where you learn from data on the World Wide Web. And pre-training involves first using a heuristic to tokenize text. What is tokenization? Well, where you take text and you break it up into symbols, okay, called tokens. Okay, so there's some finite number of tokens, and so you stream through the text and turn that into a sequence of tokens. And tokens represent words, tokens represent punctuation, and some others. Okay. So you have this time series now of symbols or tokens, and you train an autoregressive model. So you take a sequence of recent tokens. There's an autoregressive model that predicts what the next token is going to be. Okay, now the architecture of this model that's popular right now is called the transformer, just a particular architecture for autoregressive model. Actually, a very interesting one for various reasons, but it's a particular architecture for an autoregressive model. Okay, and the output is a probability distribution over all possible tokens. Okay, and this pre-training leads to an autoregressive model that can be used to generate responses to any prompt. Okay, so what's a prompt? A prompt is a text message. You could take the text message, tokenize it, plug it in here, and then you get a next token, right? You can add that to the text message and then get another next token and keep cycling through and generate a bunch of next tokens, right? As a response to the original text message. And interestingly, after training on data from the World Wide Web, you can actually generate, intelligible and interesting responses to prompts just by rolling forward with the autoregressive model. Now, this doesn't work great. The responses tend to be low quality, but it's just amazing that it works at all. Okay, so that's what comes out of pre-training. Okay. Okay, one of the tokens is an end of response token. And so the idea is you roll forward until you see an end of response token. All right. Questions? Okay. So since it's amazing that this works at all, but doesn't work great. And since it doesn't work great, there's a second step in this generative AI workflow, which is called fine tuning. And the idea is to have the system interact with humans and train on feedback. Now, there's many ways of structuring the interaction and the feedback. But the simplest one, which I'll talk about here, is where the human presents the AI with a prompt. The AI uses the autoregressive model to roll forward in generating a response. Okay, so you generate a bunch of tokens as a response, and then the human says whether or not it found that response useful. Okay, so one bit of feedback there. Okay, and then you can have some algorithm that adjusts the model, the autoregressive model, in response to the feedback to make useful feedback more probable than not useful feedback. Right, and then do that for a while, and then that improves the system. Right. Okay, so that's an example of how you could fine tune. So fine tuning is more broadly about interacting with humans and somehow benefiting from the feedback. But this is the simplest way of organizing that, perhaps. All right. So because of the scale of data and the scale of models involved here, putting these systems together requires highly skilled computer systems researchers. Right? There's huge differentiation here in how well these systems are architected by different engineers and how quickly they can get done. And the engineering aspect of this just plays such an important role that it almost dominates this area. A lot of algorithms are customized so that you can do things effectively and quickly enough with available hardware. And hardware engineers are trying to learn what's going on here and co-design in order to make the algorithms work better. Okay, so again, engineering is just such a dominant force and such a dominant need in this area. So the state of affairs is there's major investment in engineering infrastructure. And what's coming out of these engineering efforts is already recognized as a transformative technology. And with all the tinkering going on, you see steady incremental improvement. And the inertia of having a product of huge engineering investment it makes it difficult to come in and say, hey, you're doing everything differently, right? People don't respond well to that, okay? Because they want to make minor changes that'll improve the system within 3 months. Okay, But as academics, I think this is actually a place where there's a real opportunity, right, to sit in the armchair and really think about how you would do things if you started from scratch, even if your ideas won't play out for decades. What's up, Sean? You what? Lieutenant, got it. But Dean doesn't like that. The Dean doesn't like Shannon. The Shannon model does not fit in UF. No? Okay. Okay. Got it. So maybe post-tenured academics. All right. Yeah, he didn't write many papers. That's a problem. Like that's a red flag already. Okay. So all right. So in this spirit, it might be interesting to somehow frame a microcosm of what's being done here, so that we can start to think about how to analyze things. Um, and so suppose we have three tokens, right? -1, 0, and 1, where 0 represents the end of a message, right? So the messages are really binary strings, zeros, negative ones and ones. And then we have some offline data in the form of a very long sequence of tokens. Okay, so you have a long sequence of tokens that could be broken up into messages between the zeros. Okay, and we need to formalize what this means, but you could try, you could come up with some formalism that interprets this sequence as generated by a subpar dialogue system. So you could say, gosh, this is a dialogue. It's not quite, what I would want as a dialogue system, but it represents, some dialogue carried out by a system with some low level of competence. Okay, so this is, the microcosm of web data, right? You could think of all the data in the web as being one long sequence. Okay, and then after that you have online interactions with a human. And how do those interactions work? Well, you say, given a history of past messages and feedback, so this is the last message in the sequence ends at a 0, given this history. You have to select the next message to give to the human, right? And then after that, the human will add a message to this string. Okay, so that's the online interaction with humans. Okay, so this is sort of just a simple microcosm where we could start doing some modeling, start doing some thinking about, how do you think about doing, working with this data and what the fundamental limits ought to be. Okay, now clearly, this is where RL comes into. You can you can think of this as an RL problem. The RL really comes in the part where you interact with humans. So as you know, in RL, you take actions and get observations, and there are rewards associated with your experience. And actions are selected by a policy. A policy assigns a probability distribution to possible actions conditioned on history. And what you want to do is you want to choose a policy that fares well with respect to an objective, like expected discounted rewards. All right, so in our context of generative AI, you could think of the environment that the RL agent is interacting with as a human, right? And the action is a transmitted message, right? A sequence of bits ending, sequence of ones and negative ones ending with a 0 that you're transmitting to the human. And what you get back is a message from the human, again, a sequence of negative ones and ones ending with the 0. And the reward is some extra feedback you get from the human telling you whether the last message was useful or not. Okay, it's an RL problem. And so fine tuning is naturally framed in these terms. And in this area, fine tuning is sometimes called reinforcement learning from human feedback. And it's exactly because people realize that there's this connection. All right, so let me leave you with a list of some issues that I find interesting. There are many open issues in this area to think through. Um, there are modeling issues, involving what kinds of priors and likelihoods one might bring to bear in thinking about such data. Um, you know, in particular, you need to address, what is it that you are trying to learn from pre-training data, uh, how to use that to condition your fine-tuning, and also, one hallmark of this area that makes these systems work is the models are huge and very flexible, right? So that you don't ossify too much around initial assumptions. Sort of like anything that you bring to bear in terms of a prior can sort of be unlearned over time, right? And so they need somehow to frame this in a way where you start with really flexible priors, non-parametric models, so to speak. Okay, then there's active exploration. Interestingly, the current practice in this area does not estimate epistemic uncertainty. So, in these systems, there's no notion of active learning where you think about how to frame messages you send a human in order to actively elicit feedback that will be useful for your learning. That doesn't exist, right? And actually, I've been working on this, and I have one paper out, and hopefully, these systems will incorporate some of this soon. But it's amazing that this concept doesn't even exist in these systems yet. Also, the concept of sequential decision doesn't exist in these systems. The current state of the art, optimizes the next response to maximize the probability that it'll be useful, right? There's no notion that your next response is going to become part of the subsequent prompt, the subsequent input to the system, right? So, I mean, people realize this is an issue, but they're just like, wow, we got too many fish to fry right now. This is not entering the system yet. So again, a very interesting issue to think about, and really you get to the heart of, and how should we think about sequential decision in this context. Then there's continual learning and non-stationary. So right now the vision is, maybe every month or two you start from scratch and fit a new model based on additional data that has appeared, right? That's a $20 million project right now. I mean, people are designing hardware with hopes that the cost will come down. But every 2 months or so, you spend $20 million to fit a whole new model and do everything from scratch, right? So they would love to have, a way of thinking about how to incrementally adjust models constantly, so that you can do continual learning. And one of the things to address here is the effects of non-stationarity in data that's generated in the world. Okay. All right. So there's also this issue of what we're trying to learn from human feedback. So I think there's not much clarity in this space yet about that. And for example, in the current state of the art, right, the way they frame what they're trying to optimize, so they're trying to optimize the probability of, getting a positive response, like getting a human to say this was useful, for example. Right? Now if you do that, in the limit for each prompt, there should be a unique response that you provide, right? Because it's going to be a unique response that optimizes that probability. Now, there's this intuition that that's a bad idea. Like, you don't want to ossify around just one response. So there's some regularization in these systems that forces the responses to stay somewhat random, right? So it seems pretty ad hoc, right? And so one way I think about this is that, the current systems, were designed with an agglomerative mindset, where you're sort of taking all the data and figuring out how to use it, for specific purpose, which is getting your sample humans to like the responses. Where maybe there's a way to set things up uh, in what I would consider to be an inclusive framework, where somehow you synthesize all this data, and you know and your response isn't like the best response for your human, but rather it's drawn from a distribution that represents uh, the whole population of humans, so that the probability assigned to any response corresponds to the fraction of the population for whom that response should be the favorite, right? So it'd be nice to have an AI that actually encapsulates all of that, and sort of includes all interests of the whole population. But all these issues haven't been thought through carefully uh, yet. So I think these are all amazing issues to think through, and people in this room could really contribute to this. All right, thank you.